Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to just briefly pause on naming organic compounds and drawing organic compounds from their IUPAC name. In this lecture video, we are going to focus on isomers. And not only are we going to discuss what they are, but the different types of isomers. We're also going to learn how to identify whether or not we have isomers given given the structures of compounds. And we're also going to identify or learn how to draw the different types of isomers possible for specific alkanes. And so by the end of this lecture video, hopefully you guys can look at this first lecture slide, if you will, and understand this chemistry joke. So let's go ahead and start. So the first thing that we need to address is what is its definition. So what are isomers? So isomers are chemical compounds that have the same molecular formula, but the arrangement of their atoms are different with respect to each other. Okay? And so it turns out that there are three different types of isomers, and we'll learn them in future lecture videos. So the first type of isomer, I'll do this one in green, is a structural isomer. So let me zoom in here. Okay. So if you guys are looking at structural isomers, you'll notice that their actual structure, the way that those carbons are bonded with respect to each other, are different. However, if we count the number of carbons and count the number of hydrogens, if their chemical formula is the same, then they are structural isomers of each other. Okay? And so we have 1, 2, 3, 4, 5. So here we have 5 carbons. And so if you look at the top, we have 5 hydrogens. Added to the 5 hydrogens at the bottom, we have 10, 11, 12. And so here we have 12 hydrogens for pentane. And so looking at 2-methylbutane, notice that the name of the two compounds are completely different to each other. And so one might suspect that, they might not have any relationship. But if you count, once again, the number of carbons, 1, 2, 3, 4, 5, and if you count the number of hydrogens, so here there's 3, 6, 9, 10, 11, 12. It looks like there's 12 hydrogens. Now if you notice, the chemical formula for pentane and 2-methylbutane are exactly the same. And if they're exactly the same, the chemical formulas are exactly the same, then therefore these two organic compounds are structural isomers with respect to each other. So this is describing their relationship. Okay. So whenever you say that two or more compounds are isomers of each other, specifically structural isomers, then you're basically communicating to the reader or the audience that you have that those two structures have the same chemical formula, but the arrangement of their atoms are different. Okay. All right, so there's two other isomers that I'm going to discuss in future lecture videos. So geometric isomers, I'll probably discuss geometric isomers in the next lecture video, and enantiomers, that's going to be discussed in a different chapter altogether. And so let's go ahead and just focus on structural isomers. Now, another name for structural isomers is constitutional isomers. And so whenever you guys come across constitutional or structural, they're both referring to the same definition. they're synonymous to each other, and they're just basically communicating to you that these chemical organic compounds have the same chemical formula, but their structural arrangement is different. And once again, we can go ahead and determine whether or not these organic compounds are structural isomers of each other or not by simply counting the number of atoms per element and writing it as a chemical formula. And so here I have 4 carbons. Here I have 4 hydrogens plus 4 hydrogen, that's 8, plus 1, that's 9. And then last but not least, I have 1 bromine. Okay. So for 1 bromobutane, that is going to be the chemical formula. So let's go ahead and take a look at 1-bromo-2-methylpropane. If you look, their structures are completely off from each other, right? They don't look anything like each other. However, when we count the number of hydrogens and carbons and bromine, we'll be able to determine whether or not they're structural isomers of each other or not. So let's go ahead and count. So here for carbon, we have 1, 2, 3, 4 carbons. And for hydrogen, we have 3 plus 3, that's 6, plus 1 is 7, plus 2 is 9. And we have 1 bromine. Okay. Now, if you compare their chemical formulas, it looks like they're the same. And so therefore, 1-bromobutane and 1-bromo-2-methylpropane are constitutional isomers of each other. And if you guys look at a 2-bromo-2-methylpropane, here we have 1, 2, 3, 4 carbons, 3 hydrogens, 3, 3, that's 9 hydrogens altogether, and finally 1 bromine. And so zooming out and looking at all the chemical formulas that I have derived from just by looking at counting the number of carbons, hydrogens, and bromines in the structural formula, notice that the chemical formula for all 3 are the same. So all 3 of these compounds are structural isomers of each other. Okay, and so let's go ahead and ask ourselves, what would an example be of, 2 structures that are not constitutional or structural isomers of each other. So let's go ahead and go back to that joke that I kind of brought up at the very beginning. So what I'm going to do is I'm going to copy and paste this and just erase some stuff that we don't need. Oops. All right, so what I gave you guys are skeletal structures of these 2 compounds. And so the joke is claiming that, those 2 are twins of each other. And we're going to determine that. I mean, visually we can kind of see that they don't look anything like each other. But if you go back to the other examples that we've looked at, these 2 don't look anything like each other, and yet their chemical formulas are the same. And if you look at all 3 of these, they don't look anything like each other, yet their chemical formulas are the same. So maybe these 2 compounds, even though they don't look the same, they might have the same chemical formula. So we need to check. So focusing on the structure on the left, you guys will soon know that the name of this aromatic compound is benzene. We need to count the number of carbons and count the number of hydrogens. And so the carbons will represent the corners where the two lines kind of meet or intersect. And so here I have 6 highlights. So there's 6 carbons. Let's go ahead and check this guy. 1, 2, 3, 4, 5, 6. And so it looks like we also have 6 carbons. And so the next thing that we're going to look at are the hydrogens. And the hydrogens are a little tricky for the skeletal structure, just because remember that skeletal structure, that for the skeletal structure, the hydrogens are ignored. It's implied that it's there, but we have to do some quick math. So remember that each carbon, each of these pink dots, they want to follow the octet rule. So they need 4 covalent bonds. And so whatever is not shown, it's implied that a hydrogen is covalently bonded to that carbon. So what does all that mean? So let's go ahead and take a look at this carbon that I'm kind of dotting with in black. So currently, this carbon has 1, 2 covalent bonds. Now for the double bond, it does extend, okay, to this carbon. So in terms of like the sphere, okay, we have 1, 2, 3 bonds. So that means that for it to have its octet filled, there's going to be an invisible hydrogen that's typically not shown in a skeletal structure. So this would be the 4th covalent bond that central carbon needs for its octet to be full, or for it to fulfill its octet rule. Okay. And we're going to go ahead and apply that same logic for all of the pink dots that I've highlighted. And so let's go ahead and look at this carbon on the right. So notice that maybe I can do this in a different color. Maybe red will be better. So 1, 2 covalent bonds. And then this double bond also belongs to this carbon. Maybe red is not so good. Let's do green. Okay, so 1, 2, 3. Okay. And so since there's 3 bonds, and since this carbon needs another bond, that bond is going to belong to hydrogen. Okay. So if we kind of think about this whole process, I guess I'll just do a couple more just so that you guys can see. Zoom in. There we go. All right, so if you guys are looking at this carbon, there's 1, 2 bonds already on that carbon. And since there's a double bond, this is going to represent the 3rd. And so for the 4th, we need 1 more, and that's going to belong to it, that invisible hydrogen. Okay. All right. And so if you guys apply that logic for all of the carbons that you guys see here, you'll find that there's 1 hydrogen, 1 hydrogen, and 1 hydrogen. That is invisible in the skeletal structure. All right, so counting the number of hydrogens for this molecule, we have 6 hydrogens. Okay, so that's the chemical formula for this benzene ring. Now, if we're looking at this alkane or alkene, we're gonna have to fill in the missing hydrogens by counting the number of covalent bonds that each carbon currently has. And so here we have 1, 2, 3 bonds. So that means I need 1 more hydrogen, 1 more covalent bond. Here I have 1, 2, 3 bonds. So that means I need one more hydrogen. 1, 2, 3 bonds. That requires another hydrogen. 1, 2, 3 bonds. And that requires another hydrogen to make 4 bonds on the carbon. Now if I look at this carbon, I have 1, 2 bonds. And I need 4 covalent bonds surrounding the carbon. And so that implies that there are 2 hydrogens that are not shown. Okay. So same thing here. This has 1, 2 covalent bonds. For that carbon to have met its octet, it needs 2 more covalent bonds. And those covalent bonds are going to be filled in with hydrogen. So remember the rule is that hydrogens are typically ignored in a skeletal structure. Okay. And so counting the number of hydrogens, we have 1, 2, 3, 4 on the left, and then we have another 4 on the right. And so the total number of hydrogens is 8. So looking at the chemical formulas of these two structures, are they the same? So no, they're not the same. And so if they're not the same, we can conclude that they're not structural or constitutional isomers. And so hopefully that demonstrates how to go from skeletal to count the number of hydrogens to determine its chemical formula. And also, hopefully you guys understand this joke.